Now this is the first part of the lesson on permutations, and we were looking previously at some counting principles, and so we're going to expand on those in order to come up with new strategies of approaching some problems. So if you're trying to put three children represented by A, B, and C in line for a game, then the question is, how many different orders are possible? Well, if we construct a tree diagram like we did before, then we can we can see all the choices and all the possible arrangements there are. So firstly, we have three choices of who to put first in line. Once we make our first choice, then we are limited. If we choose A first, then we can choose B second or C second. Similarly, if we choose B first, then we have to choose between A and C second. And once we make our third choice, there is only one option available. So for example, if we choose A first and B second, that only leaves us with C to put in third in line. So you can see that their resulting order, there are 6 possible arrangements if we're going to put these 3 children in line. So another way we could visualize this is to think about putting a child's name in 3 different boxes on a piece of paper. For example, in the first box, we would have a total of 3 names available to put in the first box, 3 choices. And once we fill the first box, we only have 2 names left to put in the second box. And once the first 2 have been filled, there is only 1 name remaining to put in the third box. And as we said before, the multiplicative principle states that there are 3 times 2 times 1, or 6 ways of doing this. So now if we ask the question, what's the probability that a random ordering will produce the order A, B, C? Well, as we said before, there are 6 possible arrangements, 6 possible outcomes that we could have, and only one of those is A, B, C. And so the probability of randomly putting these kids in line would then be 1 out of 6, because there is only one outcome where they are in the order A, B, C. So now we're going to look at factorial notation. And I'm going to review this problem and just come up with the reason why we're going to start using this. The ordering problem in the first example dealt with arranging the names of the 3 children to create sequences with different orders. In the simplest case, we used all the children's names to fill the same number of positions. This was done by making a first choice in which all the names could be chosen. Then the second choice, there was 1 fewer choice available since the first child's name had been already selected and was no longer available. And finally, the last choice was forced on us because there was only 1 remaining name. And so, thus, there are 3 times 2 times 1 ways of putting the children in line. And we're going to write this 3 times 2 times 1 as 3 factorial. And so for factorial notation, n factorial is calculated as n times n minus 1, or 1 less than n. So in the case before, we had 3 factorial was 3 times 1 less than 3, which is 2 times 1 less than, 2 less than 3, which is 1. And this continues until you get down to 1. So as an example, if we have 5 factorial, that means that's equal to 5 times 4 times 3 times 2 times 1, or 120. So I want you to work through these questions and then check back on the solution. Now your calculator should have on it a factorial button. So if I'm going to calculate as I did before, 5 factorial, I press 5, and then there should be an n factorial or x factorial button on your calculator. So if you find that, and then press 5 and then factorial, it'll return the value of 120, which is 5 times 4 times 3 times 2 times 1. So try these questions and check your answers in the next video.